I want to turn now to what I think is the most important area when looking at security in Mina, and that is the concept of under-constrained proofs. Now this can be a critical vulnerability, and in effect what it is logic that is going to execute but isn't provably constrained. And when we're looking for this, major red flags are that there is code that is security critical but it is inside a Provable.asProver block, or there are important checks that are using non-provable types, or there is conditional logic that could alter the behaviour of our program but it isn't within the circuit. And if we want to verify this, what we can effectively do is to modify the contract code to skip checks, and the verify proofs would still be valid. And the key question to ask yourself when you're looking at the code is every security check actually enforced within the circuit? So let's look at it in a little more detail. So some of the key indicators that there is a problem of this type is that we have a Provable.asProver block containing security critical logic, or that we have non-provable types used in conditionals, or that there is logic that is critical for the operation of our zkApp that is bypassing the circuit, or we are using the requireNothing on values that should be constrained. Now I've got an example of this vulnerability for you here. So we have here our method critical operation, and what we have is a check that checks whether we're admin or not. And this is being done though in a Provable.asProver block. And then later the result from that is being used to do some sensitive action. So clearly the security critical part of this is being done but is not part of the proof. And if you wanted to test this, what you could do is to modify the code to bypass what constraints should be there and then generate a proof. And if you can still generate a valid proof after removing the security checks, the checks that we really need to be tested, then that shows us that the contract is under constraint. And that effectively illustrates the exploit that could be done. So a malicious prover could effectively generate a proof, but one that bypasses the essential security checks, but that proof could still be accepted. So let's look at the Provable.asProver in a little more detail. So this is a function that allows you to run arbitrary TypeScript, but this is run outside the circuit, outside of the circuit's constraints. Now there are valid reasons why you may want to do this, but you have to be very careful when you make that type of decision, when you're deciding what code is going to be constrained, what code is going to be part of the circuit, that you have within the circuit the code that is essential for the security. So what does this Provable.asProver do? Well, it executes code when we're generating the proof, but it is not part of the circuit. So any conditionals, anything that happens within that Provable.asProver block does not form part of the constraints within the circuit. Now this can be useful. This does give us access to things that otherwise we would have difficulty with, because it means we can access non-provable types and operations. So there is a valid use case for using this, but you have to be aware that if you're doing that, then that access, the things that you're reading and the operations that you're doing are not producing something within the circuit, so they're not part of the proof. And we can also use something in a block, a Provable.asProver block, to feed data back into the circuit, and that may be something that is valid to do. But as you saw in the pattern that I just showed you, this could be dangerous, because in the pattern I just showed you, we had something that was security critical that was being fed into another function. So some further uses for it, we can use it for debugging as well. That can be useful. It can help with complex logic. So if we have some logic that is too complex so that we cannot express this as a circuit, then maybe you're going to put this into such a block. Also, if we're interacting with the outside world and we want to interact with an external API, for example, then we could also put that into a block. But always remember that if that happens, if the code is written like that and we have something within one of these blocks, then that is not going to be enforced by the zero knowledge proof. And that means that it's not going to be verified on the network. When we send our proof to the network to be verified, there are no constraints produced by that block, and so the network obviously cannot check anything that has happened in that block. And as I said earlier, this could lead to an exploit where a prover could manipulate this situation. So in addition to developers being very aware of this, when we're auditing code, we also should be looking for the potential for this type of exploit. So from the auditing perspective then, if you see provable as non-prover blocks, then you really do need to check them and see if there's anything within them that is security critical, such as authorization checks, state validation that needs to be enforced on chain, or calculations that will determine core contract behavior. And any such logic must be expressed using provable types and operations directly within a circuit so that it can be proven.